Okay, so here we have a problem where a log is tied to an anchor and thrown overboard, and the anchor comes to rest at the ocean's floor, and the log is going to float, and we want to know the tension and the rope in between the log and the anchor. So here's how we do it. First, as always, we draw a picture. So there's the water. Here is our log. This log has a diameter D and a length L. And we'll write that information right here. Well, the diameter is 0.20 meters and the length is 0.50 meters. And we might as well indicate the density of our wood. This is going to be a hardwood. So the density, this might be given, or you could find it in the back of a book. It's going to be 750 kilograms per cubic meters. And this log is tied, make it a green rope, to an anchor resting on the ocean floor. It's not a bad anchor. The ocean floor looks like that. And better make it look like it's actually touching, right? And the last piece of information we might want to put on here is the density of salt water. Density of salt water is about 1,030 kilograms per cubic meter. Okay, now that we have a picture drawn, we're going to have to do a free body diagram. And this free body diagram is going to be for the log. We're doing a free body diagram because we're going to apply Newton's second law to this. And we need to know the forces acting on this log. First, the log has some weight, W. And because of the string, it also has some tension, T. And if those were the only forces acting here, then it would be accelerating, and we know it's not. So there's our buoyant force. And I always like to indicate coordinate system. So here's my coordinate system. Now we apply Newton's second law. We're only going to use the y direction. And since it's not accelerating, we can set this to 0. And so we sum the forces. In the positive y direction we have B, the buoyant force. And in the negative y direction we have W, the weight of the log. I'll just write it as the weight of the wood. And T, the tension in the rope. That's all equal to 0. Since we're looking for T, we can move that to the other side. I'm going to write it this way just so it's a little clearer. And now we need an expression for the buoyant force acting on this object. Well, Archimedes' principle tells us that the buoyant force is equal to the weight of the displaced fluid. So I'm going to substitute that for buoyant force. And now I need an expression for both of those weights. Tension force is equal to the mass of the displaced fluid times the acceleration due to gravity, and this is going to be the mass of the wood times the acceleration due to gravity. I'm going to factor out G for both sides. G. And for the mass of the displaced fluid, I am now going to use the density of the fluid times the volume of the fluid. So I get the displaced fluid times the volume of the displaced fluid. And I'm going to do the same thing for the wood. And now I'm going to take a look at this log. Well, the log has a volume V that is identical to the volume of the displaced fluid. It is the volume of the log that's actually displacing the fluid. So I'm just going to make a note here that the volume of the displaced fluid is equal to the volume of the log. And I'm just going to set that equal to V, which in this instance is going to be the volume of a cylinder, pi r squared times L. So we get T is equal to G times, and I'm going to factor that out since it's the same thing, pi r squared times L. And the displaced fluid is salt water, so I'll substitute that in and that in. And there we are. We've solved it for T. We have all of these variables. All we need to do is plug in our initial conditions. And doing so will yield a value of 43 newtons for tension.